Well, thanks for the introduction, and I really appreciate Oxford Instrument for giving me this prestigious prize. It's really a great honor for me. Now today, I will mainly talk about the work that I did to get this prize. Well, my son is 6 years old, and my daughter is 4. Once in a while, the little kids ask me, Daddy, you leave home early, come back late. What do you exactly do at work? This is how I came up with to explain to the little kids. Once upon a time, there was an island called Singlet Island. On this Singlet Island, there was a special creature called superconducting man. Not the Superman, but the superconducting man. Well, just like Superman, the superconducting man also have a superpower. We human beings are very interested in finding the superconducting man, learning their superpower, and building machines out of their superpower. So generation after generations, explorers have landed on this island and found many interesting things. For example, one side of the island is very hot, and the other side of the island is extremely cold. The superconducting men tend to only live on the cold side of the island, and also they're very scared of the high mountains where there are strong bar magnets, the one that we put on the fridge, but very strong. I happen to be one of those explorers. After spending many years on this Singlet Island, me and my colleagues, we decided to take on a little boat and start a new adventure. So we ended up landing on a different island called Triplet Island. And turns out we are one of the only few who have ever landed on this island. Not only that, on this Triplet Island, we also found superconducting men, but they are very different. One of the biggest difference is that they love these high mountains. As a matter of fact, the superconducting men we found live on the highest mountains with the strongest bar magnets. Clearly, they have a very different superpower. So now we're still in the process of learning that superpower. Hearing this story, the kids nodded and said, Daddy, you did a wonderful job. So today, basically, I'm going to tell you the real life version of this story. But before I start, I want to take this opportunity to appreciate all my collaborators. A lot of people, many collaborators worked on this project. And here, I will only mention those who are directly related to what I will talk today. Dr. Nick Bush from NIST is my current postdoc advisor, and he's also the captain of this little boat for our new adventure. Dr. Jean-Pierre Paglio, very important collaborator at the University of Maryland. Many scientists, postdocs, and students closely working on this project. Now, Dr. John Singleton and Dr. David Graff from National High Magnetic Field Lab helped a lot for the measurements in the high magnetic field. Dr. Matt Heaven and his postdoc in UIUC did STM work. Dr. Yuji Furukawa and his postdoc performed an NMR measurement which provided the earliest evidence for the triplet pairing. Okay, for a superconductor, there can be two kinds of Cooper pairs. A singlet pair, where two spins have different orientation, or a spin-triplet pair, where two spins can have the same direction. Spin-triplet superconductors are one of the most promising candidates for topological superconductors, and therefore are potentially useful for quantum computers. But spin-triplet pairing is a very rare quantum phenomenon. Within a few thousand superconducting compounds that have been discovered, there are only a few identified as a candidate for spin-triplet superconductor. So how do we look for another spin-triplet superconductor? Well, to be honest, we don't even have a good guidance to look for a conventional superconductor, let alone an unconventional superconductor with triplet pairing. That being said, we do have some practical guidance. If we look at the phase diagram of two high-temperature superconductors, cuprate and iron-based superconductor, they obviously share similarities. The parent compounds are not superconductor, but have antiferromagnetic ground state. When the antiferromagnetic ground state is suppressed, either by chemical doping or pressure, superconductivity emerge. So a lot of people are working along this line. Take a antiferromagnetic compound, apply pressure or do chemical substitution in order to suppress the antiferromagnetic, then measure resistance to see if it superconducts. If not, try another one. However, this is not going to help us find a triplet pairing. We know the cuprate is D wave and iron-based is S wave. Both have spin singlet pairing. This can be understood in a very naive picture. We believe that the underlying mechanism is important to the superconducting pairing. Well, antiferromagnetic has alternating spin up and spin down. No wonder it only gives this type of pairing. If we are looking for triplet pairing, we might need to look for superconductivity in the vicinity of ferromagnetism. Indeed, there are such materials. There is a whole class of materials called ferromagnetic superconductors. Well, by whole class, I really mean 3 compounds: uranium germanium 2, uranium cobalt germanium, and uranium rhodium germanium. In all these 3 materials, superconductivity coexists with ferromagnetism. If we look closely, they share one more feature. They all contain uranium, which we believe give rise to ferromagnetism. So we decided to look for superconductors in ferromagnetic compound containing uranium. Now, this is a very good starting point, because by doing this, we just shrink the search space from 60,000 inorganic compounds to a few hundred compounds. This is certainly doable. We tried different compounds. At this time, our target was uranium-7, tellurium-12. It is a ferromagnetic compound with Curie temperature at 50 K. The idea was to synthesize this compound, then apply pressure or do chemical substitution to see if it superconducts. Unfortunately, I kept getting a different compound, uranium-tellurium-2. Well, as you can see, I got very nice single crystals, very nice X-ray diffraction pattern, but what was known about this compound? It turns out uranium-tellurium-2 has been studied for decades. This is a summary of what was known by 2006. Single crystals can be synthesized, resistance, magnetization, specific heat were carried out down to 2K. It is just another heavy fermion compound with no magnetic ordering, and sorry, we don't like you as a moment. So it was a boring material, but to me, it's very interesting to see how boring this material is. Keep in mind, this material contains uranium. For those who are not familiar with the periodic table, uranium is at the bottom of the table, where everything contains unpaired F electrons. At high temperatures, F electrons are randomly oriented, but at low temperatures, system would like to release entropy by getting into an ordered state, either an antiferromagnetic order or ferromagnetic order. I really think there must be a magnetic order at lower temperatures. So I took the crystal, cooled down, and measured the specific heat. Here is the specific heat data as a function of temperature. Down to 1.8, nothing happened, just like what was reported. When I cool down a little bit further, there is an anomaly at 1.6 K indicating a phase transition. Well, what is this phase? It measures the magnetic susceptibility, and this looked like a textbook example of masonry effect. The dimeagnetism looks like a superconductor. Okay, let's measure the resistance. It does drop to 0. Indeed, it is a superconductor. Well, this discovery alone is not really earth-shaking. Superconductivity is actually a very common phenomenon. Once in a while, people discover superconductors. No big deal. But what happened next really surprised us. Okay, superconductivity 101. One of the fundamental property of a superconductor is that magnetic field suppresses superconductivity. This can be done in 2 different mechanisms. When a magnetic field is applied, it tends to flip one quartz spin to the same direction of the magnetic field. When that happens, a Cooper pair breaks. This is called paramagnetic effect. Also, in the magnetic field, Electrons move in a circular motion and therefore gain kinetic energy. When the magnetic field is too large, kinetic energy overcomes the binding energy of the Cooper pair, and the Cooper pair breaks. This is called orbital effect. Now let's see what happens when we apply the magnetic field to uranium ditelluride. Uranium ditelluride is an orthotropic system, so three axes are all different. And we first apply the magnetic field along the A axis. Indeed, superconductivity is quickly suppressed by magnetic field. Here, I plot the critical field as a function of temperature. It follows a theoretical model for orbital limit pretty well. And here is a paramagnetic limit. When we apply the magnetic field along the C axis, it starts to deviate, but only a little bit. This is what happens when I apply the magnetic field along the third axis, B axis. Clearly, superconductivity remains even up to 20 Tesla. In fact, 20 Tesla is only enough to suppress the superconducting transition from 1.6 K to 1 K. Now, if we put on the same plot, here it is, clearly it deviates from the theoretical model. In order to know how large the critical field is, we took a sample to National High Magnetic Field Lab and measured up to higher field. Here's the resistance data as a function of magnetic field. It is 0 all the way up to 35 Tesla. And then there's a sudden increase. So critical field is 35 Tesla at 0.35 K. Now, if we put on the same plot, it is here, and the paramagnetic limit is only 3 Tesla. So it's 10 times higher than the paramagnetic limit. To give you a comparison, last year, scientists found the room temperature superconductivity in the pressurized lanthanum hydride. There, the critical temperature is 250 K, and the critical field is about 100 Tesla. Now, if we scale the critical temperature of uranium ditelluride to the critical temperature of pressurized lanthanum hydride, the critical field of uranium ditelluride would be 5,000 Tesla. This is extremely high. There can be a very simple explanation for this extremely high critical field. As I mentioned earlier, for a spin-simplet pairing, the magnetic field wants to flip one of the spin and then break the Cooper pair. But if it was already a triplet pairing, the spins are already in the same direction. Magnetic field would not break a Cooper pair through this mechanism. So this result strongly indicates we actually found a spin triplet superconductor. Well, is there any real evidence? A direct experiment to probe the spin state of electrons is the NMR, the nuclear magnetic resonance. If it is spin-simplet pairing, at high temperatures, there are spin half electrons. At a lower temperature, there are spin zero Cooper pairs. The total spin will gradually go to 0. If it is spin triplet pairing, at high temperatures, there are spin half electrons. At a lower temperature, 2 spins gives total spin 1. The spin moment remains the same. When we did an NMR night shift with a collaborator, this is how it looks. The spin shows no change as function of temperature. It's a spin triplet pairing. Well, as I mentioned, spin triplet superconductor is a good candidate for topological superconductor. So, is this topological? To answer this question, our collaborator performed STM measurement. Long story short, when they put the STM tip in the middle of the sample, it shows a very nice signature of superconducting energy gap. But when they put the tip on the edge of the sample, they observed antisymmetric in-gap structure. This indicates it's a chiral surface state that is consistent with a chiral superconductor, which is a type of topological superconductor that can host marijuana fermions, and therefore it has the potential to be used to build quantum computers. So that was a really big surprise. This discovery caught a lot of attention in the community. Many groups started working on this, and a lot of papers were already published. I think the momentum has just been built, and a lot more are coming on the way. Well, at this point, I hope I made it clear that this discovery was made by accident. But by accident, I do not really mean I was having a vacation on the beach and picked up something and it turns to be a spin triplet superconductor. By accident, what I really mean is this. I was looking for India and landed on a new continent. It turns out this new continent is also a very interesting land to understand the fundamental physics of superconductivity. Again, a basic property of superconductivity is that the magnetic field suppresses superconductivity. Having that in mind, next I will show you triple reentrant superconducting phases in a triplet superconductor. Here, reentrant means die and come back to life in magnetic field. And there's not just one of this, there are 3 such phases. After this study, the National High Magnetic Field Lab wrote a report calling this a Lazarus superconductivity. I had no idea what this is. Turns out, this is a story in the Bible. Lazarus died, Jesus came and raised him from death. So next, I will show you how magnetic field raised superconductivity from death for 3 times. Okay, I already showed you this data. This is the resistance as a function of magnetic field when the field is applied along the b-axis. But I'm showing now in a logarithmic scale. Again, resistance is 0 all the way up to 35 Tesla, then there is a 5-order magnitude jump. We don't have to apply the magnetic field along any axis. As a matter of fact, we can rotate from b-axis towards a-axis. When we did this for some particular angle, first we saw 0 resistance, and there is a jump indicating normal state, and then it came back to 0 resistance again, indicating a superconducting phase, and then a normal state again. Now, in this field range, magnetic field actually helped to stabilize the superconductivity. This is called field-induced superconductivity. Now, this is a very surprising result, but it has been seen. Here I'm showing an inorganic compound and an organic compound. In both cases, in some magnetic field range, it induces superconductivity. Now, this can be understood in terms of Jacquiner-Peter effect. In this picture, there are 2 different kinds of electrons, localized electrons and itinerant electrons. Localized electrons can have ferromagnetic order, and itinerant electrons can give rise to superconductivity. If the interaction between the localized moment and the itinerant electrons are negative, localized moment can impose an internal magnetic field on the Cooper pair in a different direction. In that case, when you apply the magnetic field, the negative effect is to cancel out the internal magnetic field that is already imposed by the localized moment, and therefore it can induce superconductivity. But likely, this cannot explain what happens in uranium ditelluride. For the Jacquiner-Peter effect to work, the magnetic field needs to be along the exact direction of the magnetic moment, but we saw this in a fairly large angle range, and also uranium ditelluride is probably an itinerant system, not a localized moment. Well, in the itinerant system, it has also been observed. Here's the uranium, rhodium, germanium. As we can see, when the magnetic field increases, it first kills superconductivity and then induces superconductivity. This is probably similar to what we saw in uranium ditelluride. In any case, it's a surprising phenomenon, but it's not unique. But what I'm going to show you next is very unique. Within 60,000 inorganic compounds, there's only one such example. Okay, I showed you there's a sudden increase in resistance at 35 Tesla when the magnetic field is along the b-axis. It goes to a normal state. But what kind of normal state? To answer this question, we measure the magnetization. There's a large increase in the magnetization value, indicating a change in spin orientation. Likely, this is what happens. In the low magnetic field, the magnetic easy axis is A-axis, but there is no magnetic order. The spins are roughly along the A-axis, but not ordered. When the magnetic field is applied along B-axis and reaches 35 Tesla, all of a sudden, all the spins rotate towards B-axis. It is like a ferromagnetic phase, but induced by magnetic field. So we call this a field polarized state. Here's the entire angle phase diagram. Here's a superconducting phase, re-entrant superconducting phase, and here's a field polarized state. But this phase diagram actually hides a big secret. There is another field-induced superconducting phase deeply buried in this field polarized state. This time, we rotate the magnetic field from B-axis towards C-axis. Here's the resistance data as a function of field for 14.5 degree. If we keep rotating at 19 degree, we see the resistance suddenly drops, and at 23 degree, it drops to 0. At a higher angle, it goes to normal state again. So this is a second field-induced superconductivity, and this is the only compound in the world that shows two independent field-induced superconducting phases. And the field range for the second one is a world record. Now, Dr. Brad Bobinger, the director of the National High Magnetic Field Lab, made a comment of this study. He said, "The discovery of this Lazarus superconductivity and a regular high field is likely among the most important discoveries to emerge from National Mag Lab in its 25-year history." Okay, I promised there are 3 such phases. Well, where's the third one? The first 2 are at the ambient pressure, and the third one is under applied pressure. Here's a phase diagram of uranium ditelluride under pressure. Now, first we see the superconducting transition temperature is enhanced by twice. In the normal state, in the low pressure region, we observe the suppression of an energy scale that might be related to Kondo coherence. In the high pressure region, we observed a new phase with magnetic nature. It could be ferromagnetic phase. There's a region where superconductivity coexists with this magnetic phase. Here we see an anomaly associated with magnetic phase, and then resistance drop at a lower temperature. But if we look closely, resistance actually does not go to 0. It becomes very small, but does not go to 0. At this pressure value, if we apply magnetic field, resistance does go to 0. So field-induced superconductivity again. Having one of these phases is surprising. Having 2 such phases, astonishing. Having 3 such phases, that's too good to be true. Actually, last year on a conference, an expert came to me and said, "You better stop working on this. If you report another field-induced superconductivity in this compound, we're not going to believe you." Okay, I'm gonna stop here, but I believe more surprises are coming on the way. Let's enjoy. At the end, I want to mention that next month I will join the physics department of Washington University in St. Louis as a faculty member. I will keep doing research in the area of quantum material, and hopefully I can bring more excitement to the field. Thank you.